Welcome to the distributed system course. Today we are going to discuss some topics and algorithm related to the issue of how process coordinate their actions and agree on shared values in the distributed system. One of the advantages of distributed system is resource sharing. That is, each node in the distributed system can share their resources with other nodes. So there is a need of proper allocation of resource to preserve the state of resource and help coordinate between the several processes. We have to achieve mutual exclusion among a collection of processes so as to coordinate their action with the shared resource. If a collection of processes share a resource or a collection of resource, then the mutual exclusion is required to prevent the interference and ensure consistency when accessing the resource. That is called a critical section problem. Mutual exclusion is a concurrency control property which is introduced to prevent race condition. That is, the output depends on the order in which the processes are executed. It is the requirement that a process cannot enter the critical section while another process is currently present in the system or currently executing its critical section. Then that is we are allowing only one process to enter the critical section at a given time. Mutual exclusion we can achieve the mutual exclusion in single system or in the distributed system in different cases. If you are comparing the mutual exclusion in single computer system and mutual exclusion in distributed system, in single computer system, memory and other resources are shared between different processes. The status of the shared resources and the status of user is easily available in the shared memory. So with the help of shared variables, or we can say that by using the semaphores, mutual exclusion problem can be easily solved in particular single system, a single computer system. But in the case of distributed system, we neither have shared memory nor common clock. That is a problem. So in the case of distributed system, there is no common clock and a shared memory. To eliminate the mutual exclusion problem in distributed system, the only solution is message passing. So we are using message passing to achieve mutual exclusion in the distributed system. A site in the distributed system do not have a complete information of a state of the system due to the lack of shared memory and a lack of common physical clock. It is one difficulty in distributed system, so we are using message passing to achieve the mutual exclusion in distributed system. There are a number of mutual exclusion algorithms available in the system in our system. Some of them are Lambert's algorithm, Ricard-Agarwal algorithm, Mikawa algorithms, and Suzuki-Kasami broadcast algorithm. We will discuss each and every algorithm in the coming section. This section is to give a introduction to the mutual exclusion. Next, the approaches for this distributed mutual exclusion, that is, as we all know, shared variables or local kernel cannot be used to implement the mutual exclusion distributed system. Message passing is the only solution to the mutual exclusion in distributed system. Based on the message passing, we can group or categorize the mutual exclusion algorithms into three groups. The three basic approaches based on the message passing to implement the mutual exclusion in distributed systems are token based approach, non-token based approach, and a quorum based approach. First of all, we will discuss the token based algorithm. That is, in token based algorithm, a unique token is shared among all the sites. That is, we have a set of sites in the distributed system. We will share a common unique token to all the sites. If a site process the unique token, it can enter or it is allowed to enter the critical section. So only if a particular site can have a particular unique token, then only it can enter the critical section. This approach uses sequence number to order the request for the critical section. That is, we will use some sequence number to identify the old critical section request and the current critical section request. This approach ensures mutual exclusion because the token is unique in the system. One of the example of token based mutual exclusion algorithm is Suzuki-Kasami broadcast algorithm. Here in token based we are using one token. Based on that token, that particular site can enter the critical section. In non-token based approach, a site communicates with all other sites in the distributed system in order to determine which site should execute the critical section next. That is, if a particular node want to enter the critical section, then it will send the request to all other nodes and then finally enter the critical section. This required exchange of 2 or more successive round of messages among the sites. In the case of non-token based, if the particular token is available, the node can enter the critical section. But in the case of non-token based approach, there are several messages needed to confirm that all other nodes are not in the critical section. This approach uses timestamp instead of sequence number to order the request for the critical section. Whenever a site makes a request for critical section, it gets a timestamp. The timestamp is also used to resolve the conflict between critical section requests. All algorithms which follow non-token based approaches maintain a logical clock, that is Lembert's logical clock. The logical clock get updated according to the Lembert's logical schemes. The main two examples that is based on a non-token based approaches are Lembert's algorithm and Rickard Agrawala algorithm. The next approach is quorum based approach. Instead of sending requests to all the other nodes in the system, in the case of quorum based approach, we are sending the request only to the subset of the sites. That the subset of site is called quorum. Each site requests only a subset of site which is called a quorum. Any two subset of sites, or we can say that quorums contain a common site. That is, the system contains a number of sites. We are grouping into subset. If we take two subsets, it contains a common sites in those subsets. This common site is responsible to make sure that only one request enter the critical section at a particular time. This is the responsibility of the common site. Make sure that only one request execute the critical section at a particular time. One of the example of the quorum based approach mutual exclusion algorithm is Mikowa's algorithm. Next, we are going to discuss the requirement for mutual exclusion algorithm. There are three requirements for mutual exclusion. There is first one is safety property, then second one liveness property, and the last one is fairness. The safety property deals with the mutual exclusion actually. At any instance, only one process can execute the critical section, that is make the safety property. Only one process is in the critical section, then we can say that it is our system, our mutual exclusion algorithm satisfies the safety property. The second requirement for mutual exclusion algorithm is liveness properties, that it depends on two parameters, that is deadlock and starvation. It deals with deadlock and starvation. If this particular mutual exclusion algorithm don't have no deadlock, that is it does not have that no deadlock and starvation, then we can say that the particular mutual exclusion algorithm satisfy liveness property. You know, the deadlock, in the case of deadlock, no process is executing its critical section. Then on the based on that is two or more sites should not endlessly wait for messages which will never arise. That is, endless waiting should be avoided. That is about non-deadlock. Then the second is, that is starvation. Every site who want to enter critical section should get an opportunity to execute it in finite time. That is, a particular site send a request to enter the critical session, then after some finite amount of time it can enter the critical session, then we can say that there is no starvation. Any site should not wait indefinitely to execute the critical section while other sites are repeatedly executing the critical section, then we can say that there is no starvation. The both the non-deadlock and non-starvation deal to the success of the liveness property. The third requirement for mutual exclusion is the fairness. Each process get a fair chance to execute the critical section. The fairness property generally means that the critical section requests are executed in the order of their arrival time in the distributed system. We will follow the arrival order of the request, then we can say that the fairness is in our distributed system. That is about the requirement. Also, in the case of failure, it should be able to recognize it by itself in order to communicate functioning without any disruption. That is, the particular mutual exclusion algorithm should follow the fault tolerance also. Then the next we will discuss the metrics for performance metrics for distributed algorithms. That is, the performance is generally measured by the following four matrices. That is, there are message complexity, synchronization delay, response time, and throughput. First we will discuss the message complexity. That is the number of messages required per critical section execution by a site. That is the number of messages needed to enter for a critical section. That is, we can say that number of messages per critical section is the message complexity of a particular algorithm, mutual exclusion algorithm. Then the second performance matrix is synchronization delay. After a site leave the critical section, it is the time required before the next site enter the critical section. It is the time. That is the last site exit at a particular time. You can see in the figure that last site execute at some time, point of time. Then after some times the next site enter the critical section. The gap between the last site exit the critical section and the next site enter the critical section is called the synchronization delay, or it is the interval between the leave of a particular last process from the critical section and the next enter of the new process into the critical section is called the synchronization delay. The next parameter, next performance metrics is the response time. The response time is the time interval a request wait for its critical section to be over after its request message has been sent out. That is, it is the interval between the message has been sent out and the completion of the critical session. Here you can see that critical session requests arrive in particular time. After some time, the request message is sent out. Then after the message has been sent out, it should wait for some times to enter the critical session. Then it get the critical section. After sometimes it execute its critical section, then it complete and leave the critical section. So the response time is the interval between the message sent out and the exit of the critical section. That is that difference, or the gap is called, the time difference is called the response time of a particular mutual exclusion algorithm. The last performance metric is system throughput. That is the rate at which the system executes a request for the critical section in the is called throughput. That is the number of, or rate at which the system execute a request for the critical section. It can be calculated based on the equation, that is 1 divided by SD plus E. Here the SD is synchronization delay and E is the average critical section execution time. By using these two parameters, we can calculate, or we can determine the throughput of the particular distributed system based on some algorithms, based on some mutual exclusion algorithm. This is about the performance metrics. In the next section, we can see the mutual exclusion algorithms in detail. Thank you.